planetary surface analog simulation in Hawaii. Thanks.
Good morning, everybody. So I reported on this last year, and so this year I'm going to give you an update about what we're doing over at High Seas. And as you just heard from Kelsey and Jake, there's a number of important aspects to analog field studies, and the first two talks this afternoon deal with that as well. And so we're situated right in between those. I think it's very appropriate because this dovetails into that quite well. I'd like to, let me just recognize my co-authors, Jake and Scott Rowland, Sarah Fagents, and Kim Binstead, who's the PI of the project. So as we push out further in the solar system, we're going to have longer and longer time delays back to Earth, and this is going to necessitate more autonomous crew operations. So for example, if we're going to Mars, we have a one-way communications time on the order of 20-something minutes. So as you do that, you can't have real-time communication back with Earth. And so this has been a recognized problem for some time. For example, in the Global Exploration Roadmap, I just pulled out a number of quotes here that pertain to this. For example, demonstrate autonomous crew operations and explore landing sites of interest for extended durations, and conducting high-priority science benefiting from human presence, characterizing human health and performance, and demonstrating extended crew mobility in habitation systems. Now, these things are all relevant to the High Seas project, and these are all strategic knowledge gaps that we're trying to fill with this research. So what is High Seas? Well, it's a project, again, on Mauna Loa, Hawaii, and it's meant to mitigate risk on these long-duration, high communications latencies missions. So we have a high-fidelity mission profile and the environment as well, as I'll talk about in a moment. And the site is very unique because being in Hawaii, it allows year-round studies. The weather is appropriate so that you can have year-round isolation studies, unlike other places like Devon Island, for example, where it's too cold. It's near airports, which are easy to get materials in and out as well. Near hospitals, for example, if there's emergencies as well. We have astronaut-like crews. The selection process is very similar to NASA's process. In fact, some of the same people are involved with the selection of High Seas analog astronaut crew members as are involved with the JSC selection process. And the whole point and the way this project is couched is in terms of tracking crew cognitive and team performance through collaborative tasks. So the project is very much a human factors driven endeavor. So analogs, as we just heard, are very useful for testing out problems in the field, figuring out what works, what doesn't work, integrating systems together, getting your operations and your technologies furthered to the point where then you could start thinking about testing them in a space environment. You can do it on Earth much more cheaply and much more efficiently than you could any other way. And here's a picture from desert rats. So now, High Seas has been around since, well, it started back in 2012, and we had our first mission in 2013. Now, since that point, we've actually, is this working? No. Anyway, so we've had 3 missions at High Seas to date. We just did a 4-month mission, and another 4-month mission, then an 8th month mission was concluded just about a month ago. And there's a 12-month mission which begins next month. So this is a very progressive project. The missions get longer and longer. In fact, we just got 3 more years of funding from NASA to extend this out to 2019. There will be more missions beyond Mission 4, which is about to start. So where is this? Well, it's on Mauna Loa, like I mentioned, which is about 2,500 meters. It's about 2/3 of the way up the mountain. This is a disused quarry site. There's a picture of it here. One nice thing about this is it's disturbed already and makes it easy to permit and easy from an environmental impact standpoint as well. There's almost no vegetation there, as you can see from the photo. There's been no photoshopping done here. So it's very realistic looking to the astronauts, which is important because this is primarily a psychological study. A number of textures, complex flow history there. There's the USGS map down on the bottom showing all the different flows. These are mostly from the mid-1800s to mid-1900s. Now there's a lot of features there. There are skylights, there are channels, lava tubes, tumuli, for example, inflationary features like Jake mentioned. So there's a rich array of these things to go out and explore and map. So to get the crew ready for this, we do about a 2.5-day training exercise with them. What we've done is distill down the NASA Planetary Volcanology Field Workshop that the University of Hawaii has done for several years into that small amount of time. We go out there with them. We have them look at a number of orbital imagery maps to integrate what they think the interpretation should be for the flow units. They go out in the field, they map these units, they learn how to use the Bruntons, for example, and how to use all the equipment and the GPS. And this is good because not all the crew members are geologists. In fact, often they're not at all. They're a mix of engineers, of doctors, of various professions. You know, and if we're lucky, we get a geologist on there, but not every mission. So this is a way to help bring them up to a level of understanding before the mission begins. So how does the mission work? Well, what we do is we assign tasks to the crew that are geology related, and then the crew has to come up with a plan how to achieve that task. And they come up with a plan, they share it back with us on the mission support team on the ground. We evaluate this task, we might have some back and forth feedback with them, and then we approve it. They go out and they do their EVA or multiple EVAs to collect the data they need, the samples, the data, for example, and then they submit the reports to us. And we read these reports, we learn from them, and then we iterate and decide the next task. We give it to them, and it continues throughout the mission. This is all done without real-time communication, I should mention. We have a 40-minute delay built in to all the comm circuits that we use at high seas so that it's Mars-like. So what are these tasks like? Well, they're all team-oriented, okay? This is not something you do alone, and that's important because the psychologists behind the study want to gauge team performance and cohesion over time. They want to compare across all these missions. For example, does performance start to degrade as you go from 4 months to 8 months to 12 months and beyond, or does it not? So they try to tease out questions like that. Now, these tasks are progressive. We start very simple. And then we build upon that and get more complex, okay? And we also try to make them logical in terms of if you landed on Mars, what would you do first? And then what would you do second if you're starting to explore your environment? So the metrics are all quantifiable, you know, GPS tracks, for example, or point measurements of volume or density of rocks, for example. These sorts of things are easy to measure and compare. And we compare across missions, as I mentioned. We tend to give these to them every 2 weeks, and then they do the project. It takes about a week for them to do the project. They get back to us with the reports. And like I said, we don't really tell them how to do it. We just tell them what to do. So I'm going to give you some examples now, just show and tell about some of what these tasks are like. For example, when they just land on Mars, if they want to learn about their backyard, where are they? So here's where the high seas habitat is on the red dot. And they're located right next to this long string of spatter cones. And so we have them go out there and get the volume of this feature. How tall is it, and how big is it? How much mass of material is basically there? It gives them a good exercise with exploring, with using their equipment, their GPS, etc. One thing we do after that is we tell them to collect a lot of samples and tell us what these samples are made of, essentially. And so one thing they do with that is get the density, and it's a good chance to use the Habitat's lab equipment, and so forth. We also had them map some geologic cross sections, get some good experience with you know, in the field measurements, as well as you know, taking off measurements from photos and whatever techniques they come up with for that. And there's one of their cross sections drawn there. So one of the big exercises we have them do, again based upon that planetary field volcanology workshop series, is we have them first map, before they even go there, we have them map the area from the aerial imagery first, and you know, using infrared, using thermal, UV, etc. And then they go out there and they ground truth their map, and they see the relative sequence of these flow units. They see how close they were in making their map. They all find it very rewarding. It's the feedback we've gotten, and there's an example of one of their maps there. Like I mentioned, there are some tumuli there, and we have them go walk around, measure the height, the volume, the width of cracks, etc., and the azimuth of all these features, and send them back to us as well. So one of the other big themes of the project is lava tube exploration. There are a number of tubes around the high seas habitat. Here's a picture of if you can just make out one of the crew members at the top of the tube, and we have them go out there and measure the height, width, depth, the thickness of the rubble at the bottom, the thickness of the ceiling, etc. And we actually have them go inside a tube and map the whole tube system as it progresses across the field and the skylights that they encounter along the way. And there's one of the cross sections there that they have. And so it's a very useful exercise. In fact, we put that to use in a really novel scenario here where there's emergency simulation. And we don't tell them this ahead of time, so please don't share it with them right now if you know any of them. So we tell them there's a solar flare coming, and you have 6 hours or to go get all of your equipment and go put it in one of these lava tubes. And they have to act quickly. They have to create their evacuation plan, their materials list, et cetera, and get it all out there and wait for the all clear. In fact, here's a picture. One time they were in there with this tent, which served as their pseudo emergency shelter. And the crew actually enjoyed this. We did this in the mid-mission, 4 months into it. When, as you might imagine, it's pretty monotonous on a long mission like this. They enjoyed getting out for a little while, and even if it was in a tent. So along the way, you might imagine things break. And when you're out there on a mission on Mars, for example, there's no Home Depot. So they have to fix their own equipment. They have a 3D printer. They have the 3D print, innovate whatever designs they need. For example, they had to fix a helmet once, and this is what they did. And their backpack system that recycles the air occasionally breaks down. They have to fix that as well. So that's not related to geology, but I thought you guys might be interested. Finally, we actually have them do crew-led projects as well. They bring their own research into the mix, but in addition to that, later on in the missions, we start to give them more leeway, and we say, okay, now what do you think you should do next? What would you like to explore next? So we did that in this last mission, and here they are, and they said, well, we want to use our field spec and go out, and we want to measure how the spectra vary among all these samples along this spatter cone feature. And we want to see if the different flow units have different patterns here in the spectra. And so that's what they did, and they got good data there. There's a little shot of it at the bottom. And we came back and said, this is nice, but how does it vary with sun angles? So we went back and forth, and they did another EVA with different sun angles on it. And it was a good way to collaboratively work together while still giving them most of the autonomy. Some of the other things we're looking at now in the analysis are looking at their planned versus their actual GPS tracks and from their traverses, and why they deviate and all of that. So that's something we can do. And going forward, in the next mission coming up, there's a geophysics component that we're going to integrate into it, looking inside the lava tubes from above. Like I said, there's more missions coming. So there's a third High Seas grant was funded by NASA, and we're going to continue to study this project. And we welcome any collaborators who would like to work with us. If you have an instrument you'd like the crew to test, for example, that's possible. So thanks for listening, and I'm happy to take questions.
Any questions for Brian? Well, I have one. I was on a mission simulation, and the whole crew died at one point or another. So,
Yeah.
Are there any fatalities in your crew?
Well, no fatalities, thankfully. The IRB would really kill us if that happened. But no, we did have one crew member who had a medical issue, though, and had to leave the mission early. So that did happen, and we had to adapt and finish out the mission with 5 instead of 6 crew members. Yeah.
Microphone. They're recording.
Brian, I have a question. I've done team building for Outward Bound and places like that, so I find team building in remote environments very fascinating, part of my job. How did you handle team building?
Well, we actually went on a NOLS course, although Outward Bound is great as well.
Yeah, NOLS is awesome.
So we did that's in fact part of the selection process too. So we go on the NOLS course with 9 finalists and go out there for a couple of weeks in the wilderness with the NOLS leaders and go through this team building process and leadership development process and come back. And from that, we narrow it down to the 6 actual crew as well as the commander selected from that too. So that's how we use that through the process, but it's very helpful.
And so a fascinating thing as well for team building is from a personal lessons, team building over time, been an instructor for 10 years, degradation of team building or group cohesion, especially when you're making critical decisions, can happen if over time, overconfidence. You start blowing the basics, right? You think you know each other really well. And so you stop doing check-ins like you might do mechanical, like a mechanic might stop doing his basic checklist,
Sure.
right? What did you find over time for team building? So NOLS and Outward Bound has like core checklists. in the morning? Like,
Right.
are you a morning person, night person, to how you handle conflict, what your personality is? Yeah, what did you guys find over time?
Well, we actually compared during one of the earlier missions. We compared a checklist that we made ourselves versus one that came from JSC that the astronauts actually use at the end of their days. And we ended up adopting the NASA one later. So, but every day the crew does a debrief. They fill out the checklist. It's one of the many surveys they fill out, and it gets cataloged. And I can't comment directly on the results because it's still being worked on. But in general, I could say that there are distinct phases of the mission where you can see everybody's very motivated in the beginning, does great, performance is high, starts to slack off in the middle. They start to get they miss home, a little more apathetic, if you will, and a little bit less cooperative and less compliant with the surveys. And then, it picks up at the end as they see the light at the end of the tunnel.
Cool, thank you.
We're going to have to stop